So next thing is all these red lines, and you can guess what these red lines stand for. These red lines actually stand for the control inputs, and yeah, control inputs, not really outputs. So it's not it's not really going to be bidirectional. I mean, I could have not used these bidirectional lines, but I have another where to make it vanish. But always think that the red inputs are from the outside world to these components, not really from the component to outside world. Okay, so this is where these arrows get vanished, but always remember the case that they are not coming from the control bus, not coming from the component to the control bus, but rather control bus is a bunch of signals, and those bunch of signals are going to be selectively fed into individual components. So this control bus is a collection of bits, okay, typically called control word. So this is what I think we have discussed in the last class. The bits that are there in the control bus is going to constitute of the control word. The specific control word is going to tell us that at this point of time, maybe the program counter should be writing to the common bus, and the memory address register should going to be listening to the common bus, or the memory is going to write to the common bus, the instruction register has to read from the common bus, or the program counter has to be incremented, right? Or the program counter should not be incremented, it should be frozen, right? Or the program counter has to be loaded by a value that is available in the common bus. Okay, sometimes it is not always that we are going to increment the program counter by 1. Sometimes I want to have a function call, or I want to do a go to a different place, right, in your program, which is somewhat relatable to a jump instruction, or you have used this go to statements, right, where depending on the condition you jump to a different place, you transfer the control of the program to a different place in the program. So in those cases, the program counter is going to be loaded by where it jumps to. Okay, so there is a necessity to control that as well, and the control bus has dedicated bits for doing that. Okay, so then the logic that is going to do all these things is the heart of your the control of the CPU, which is called the CPU control or control signal generator, right? So this is by far one of the most important thing that makes this entire thing happen in a specific sequence. Okay, so you can relate this to uh, something like a puppet dance, right? So the puppets individually can't really do much, but it's about the strings that are attached to the puppets, and the person who is making this dance happen is pulling the strings in a very specific sequence that makes this entire thing look beautiful, right? In our case, this entire a program is executed on the computer, right? You can't really uh, do anything which is out of sequence, right? So if you want to even execute an instruction that says, let's say, there's a typical data movement instruction called move. Okay, so move instruction is typically associated with moving the contents of one register to another register. So you can have an instruction called move a comma b. Okay, so now if you think how this instruction is going to be executed on his computer, right? It's very easy to realize what is going to happen. The content of register A is going to be loaded in the register B. It's not a big deal, right? It's trivial. Even for many of us, even if I say add A comma B, it is trivial, right? But there are things that has to be very strictly followed. The timeline of the different events that we are going to have to achieve this move a comma b uh, has to be pretty well defined and pretty strict. Not only that, we are not really making this entire hardware to just support move a comma b, but this is going to be a general architecture that is going to support a lot of other instruction, maybe 50, 60, 100 instructions, right? Or sometimes even hundreds of instructions is going to be supported here. So we need an architecture which is a little bit more generic and not just optimized to support one particular instruction or a few instructions. So we have already looked at one generic thing, which is the fetch. So irrespective of what instruction is going to be executed, the instructions has to be fetched. So that fetching is the first thing that the control is going to do. Okay, so suppose it fetches this instruction called move a comma b in the instruction register. So move a comma b, or the machine code equivalent of move a comma b, is going to be loaded in the instruction register. After that, the instruction register is going to tell the control signal. As you see, this arrow goes to the control, and it tells that, oh, this is a move instruction, and for doing a move instruction a comma b, you need to make sure that a and let me clarify what move a comma b means. Move a comma b could mean that a is going to be loaded by the contents of register b. Okay, depends on your definition. I mean, depends on the architect how they define the nomenclature. It's not very important. It could also be a to b, but the definition has to be given. In my case, I'm saying that move a comma b. In this case, it means that b is the source register and a is the destination register. Okay, so if a is the destination register, in my definition, the control in the control bus, the signal for register a reading has to be high, because see, this register a is reading, right? That means it is actually allowing inputs, whereas register b is writing to the bus, right? Reading from bus, writing to the bus, which is basically out. So b is writing to the bus, its an output is enabled, and for a the input is enabled. If you do vice versa, it is not going to end up in the proper thing, right? And not only that, everybody else has to be silent at that time when register a is reading. Program counter or memory address register or memory or register c, nobody should write. ALU, nobody should write to the common bus. One and only person or the component who should write to the common bus at that time is b. B is given the explicit permission to write to the common bus and nobody else. Okay, so this is nothing but this control signal is going to be updated. You know how to write a basic control word, right? By now we are going into much more details. We are going to do that later, but at least for now you know what is this control word. Every component is going to have some control bits, and those control bits should be turned on or turned off, and the collection of all these control bits together is called the control word, and this control word is regulated or maintained by the control generation of the control signals. So after you fetch this, you have to sometimes you need to also decode in the sense you need to decode the fact that this is a move instruction and not an add instruction, for example, or not a subtraction instruction, not an or instruction. So this is typically called instruction decoding. And sometimes you also have to do operand decoding, means if you have an immediate thing like instruction, let's say add 7, right? Or let's say you want to add the value of a particular register to the accumulator depending on your instruction set architecture. In those cases, you also have to decode the specific operand that you are trying to use. Okay, so that is also important. So you need to decode the instruction as well as decode the operand. Okay, and after that you execute it. So execution is the last phase where you really execute the instruction. fetching and decoding is a part of the instruction execution, but not really the execution. The execute part does the job, right? Which is typically, I would say, simpler, right? Execution is going to be some combinational circuit operation in the ALU. If it is not a data movement operation like move and all, if you want to do an add, if you want to do a subtract, multiply, divide, whatever, right? If the ALU supports it, this is typically a combinational circuit operation, and that is going to be completed in one clock cycle. Okay. There could be instructions that require multiple clock cycles for the execution, but yeah, for now I am going to keep the discussion trivial, specific to trivial kind of computations like add, subtract. Okay, so just to be clear, our ALU is going to support add and subtract. You can always extend it, but for now we are going to be restricting ourselves to those two things that the ALU can do. Okay. Okay. So now you have one more thing which is typically called the status register. Status register is really useful for a lot of things, particularly what is there any classification of the value that has been just computed on the ALU? For instance, is it if the result is 0, right? So these are specific classifications, right? So these are called status flags. Okay, here I have shown two flags. The NC and NZ are complements of Z and C. Z refers to 0 flag. What is a 0 flag? If the result of a computation ends up in the value 0, right? And don't think that every instruction is going to affect the status flags, right? This is very important. Not every instruction affects all status flags. This is important to note, right? If you do a move instruction, say move a comma b, move a comma b has nothing to do with setting a status flag for 0, right, or not 0. NZ is not 0. Okay, right? So if you do a addition or if you do a subtraction, right, or if you do an AND operation, it makes sense, right? So it makes sense that suppose I have done 5 minus 5 and the answer is 0, the status flag for 0 is going to be set, it is going to be 1. So Z is equal to 1 means the computation that has just been done on the ALU resulted in the answer being 0. And the other thing is called carry, right? So often you will see that once you add two numbers, it creates an output carry, right? So if you are doing a 4-bit operation and you are trying to add, let's say, uh, 8 and 9, right? The answer is going to be 17. Okay, so there will be a output carry which is beyond 4 bits, right? Because with 4 bits we can go only up to 16 15 0 to F, right? If you want to express decimal 16 or decimal 17, the output carry is going to be set, right? So you will basically have an additional 1 which is cannot be contained by the register, because the registers are going to be specific to 8 bits, let's say, or 4 bits in the right now whatever example I've given. The extra bit is going to be 0 or 1 depending on whether you have an output carry or not. If not, this is not carry. Okay, so you can always think of this C and NC to be complements of each other, and Z and NZ are complements of each other. Okay, so for every instruction it is going to be told by the instruction set manual that whether this is going to affect a specific flag or not. Okay, so this is about the status flags. Now you can ask me that why do you need to do all these things, right? So why do you need a zero flag, right? So typically these are used to check conditions, right? For example, you are saying that, let's say if I do 5 minus 5, it results in a zero flag being set, right? And this zero flag being set is an indication or a condition to do something else, right? Where is this going to be applicable? So we often do some high level, in the high level language we actually write things like, if let's say x equal to y, do this, right? Else do this. Okay, if you really think of this being executed in the hardware, this is typically checking whether x minus y is equal to 0 or not, right? This is a comparison between x and y, and if this comparison being successful means z flag is being set, right? And if this z flag is being set, you can take this particular bit, right, and put this into some kind of a, let's say, like a multiplexer, right? The z tells you if z is equal to 0, you pass some data, right, let's say to the program counter. If z is equal to 1, you pass some other data to the program counter. Let's say the program counter is going to be loaded by the address of the next instruction. If x equal to y, this basically means that z equal to 1, right? So 0 flag is going to be set. So in this particular case, z is equal to 1. So if z is equal to 1, the multiplexer is going to pass the value of the next as the, is basically just a regular increment, right? So it's not going to do anything else. Whereas if z is equal to 0, which means the 0 flag has not been set, then it is going to load some other, so whatever is the address of this instruction is going to be loaded in the program counter. So you need to make the hardware intelligent enough so that it can act upon the values that are set by the status register. Okay, so that is the reason we need status register, particularly for doing some condition checks and executing the or changing the control flow of the program based on some conditions. So typically these are going to be used for conditions. And note that I have again expressed a very simple status register. In a real world, you have many such flags like parity bit. It could be an odd parity, it could be an even parity. Uh, there could be an overflow, right? Integer overflow and so on. So in an ideal case, you have more number, in a real case rather, you have more number of status flags and the status register has more number of bits. Here we are just showing you a small example. Maybe we are going to restrict ourselves only to z and nz so that we can at least show you something like this, right? And that is it, right? You can always extend the design to have more and more complicated, or rather more useful flags that your program or your software needs, right? There is not such much of a point as to create these conditions or unnecessarily make the hardware complicated. You need to make sure that the software that you are writing makes use of these features, right? That is why it is very important for a low level system programmer to understand what the processor has to offer. If you do not know what the processor, what kind of flexibility does a processor has, it will not be possible to write efficient code, right? Every processor architecture is going to be different, right? x86 from Intel is one kind of a processor architecture. You have MIPS architecture, you have ARM architecture, you have Sun Spark, right? Sun Microsystems had their Spark architecture and so on. Every architecture is going to have its own pros and cons, right? Own flexibility and so on, right? And the programmer, the low level programmer, has to make maximum use of the facilities provided by the underlying architecture. Okay, and recently you have the RISC-V architecture, which is an open standard for this for ISA or instruction set architecture. You have to follow a certain mandated set of instructions or in a certain pattern. They basically tell you the list of instructions that needs to be supported and the way the instructions is formatted, right? And as long as your microarchitecture implementation of that ISA is compliant, you make a RISC-V compliant CPU. Okay. So last but not the least, you may have some display options, right? So whatever is going to be computed on the CPU can either be stored in the memory, right? Or it could be directly put to a display. So there is a small point that I want to mention here. So display, as you in a real world, is nothing separated with respect to the memory. Here I am doing it just for a simulation where from register C I want to put the value to some LEDs which is going to be used as a display. But note, in the real world, display devices are also going to be reading the data from memory. Okay, so whatever the processor does, the processor has to write to a part of the memory which is typically called a display buffer, and the display buffer is going to be used by the display device. So let's say you have a monitor. The monitor is going to read uh, data from the display buffer, which is a piece of the memory, and that piece of the memory is being populated. The video frame, for example, that is going to be rendered in the screen is written, right, by the CPU. Okay, now that technology has uh, progressed a lot. There is a lot to do with just to with respect to the display buffer, how it works, and so on. For our interest, right, in this particular course, we are not going into the intricate details of how like the display graphics driver works. We will assume that in the real world it's a part of the memory that the CPU has to update, or we can do whatever I have shown here. A display is just a set of hexadecimal 7 segment LEDs that are directly connected to a register. So whatever you write to register C could be also displayed uh, in the intended displays, whatever displays we have, right? So this is typically the overall skeleton of the computer that we are going to design. And next we are going to look into something called instructions, right? And how we are going to architect instructions for our computer. Once we set that, we can start designing the computer very specifically, right? For very specific purposes, we can start writing software for our computer. So the next thing that we should look at is we will define the instruction format, right? How the instructions are going to look like in our computer, very important, right? It is for our Gajendra 1 computer, not a generic computer, right? So everybody who is going to design a computer is going to define their own instruction set format, right? So we will define the format. We are also going to define the type of instructions that we are going to support, or the various instructions that we are going to support. And after that, we are going to look into a few sample programs that are implemented using our instruction set. For example, if you have 5 numbers in memory A, B, C, D, and E, suppose I want to compute a number which is A minus B plus C minus D plus E, right? So it will be like add A, subtract B, add C, subtract D, and so on. What is the equivalent program, assembly level program in our architecture for doing that job, right? Or let's say I want to have the sum of 5 elements that are stored in memory, right? Let's say you have an array which is a contiguous set of memory locations of size 5, and it has 5 numbers stored in it. I want to find out the sum of a0 plus a1, a2, a3, and a4, right? So and store the result somewhere maybe, right? So we are going to do this kind of we are going to write this kind of program so that we have a feeling of what kind of programs we can write and how these programs to some extent they get executed. So once we get familiar with the software part of it, then we are going to go ahead and design the actual computer. So this is some broad picture that we have given. After that, once we understand how programs are going to be written for this computer, we are actually going to implement this computer piece by piece. And I am going to show you the details of the simulation in circuit words, and you are expected to try this design out on your own. Okay, and we will give you enough support to make it happen. Okay. So in the next lecture, let us start with the uh, software programming of Gajendra 1. Okay. So in the last lecture, we have looked into the overall architecture that we are going to design as a part of this course, which is the Gajendra 1 architecture. And this closely resembles, just for your reference, I want to mention, although it's not going to be exactly equal, but it is going to closely resemble a textbook architecture which is called the simple as possible computer, or SAP, right? It's called the simple as possible, which basically means it's a very simple architecture, SAP. And this has some versions like 1, 2 and 3. These are chapters. So SAP 1 is very simple, as you will see. Then there is an SAP 2 and SAP 3. What we are going to do is kind of a combination of SAP 1, SAP 2, and maybe something that is not a part of SAP 2. We are going to extend that, right? But as far as your reading is concerned, it's better to refer to this textbook, because our intended textbook, that is Harris and Harris, if you look at chapter 6 and chapter 7, they are going to primarily deal with this, but they are a little bit more involved, which is targeted towards a mainstream computer architecture course, right? So this is not a architecture course per se, right? What we have done is a lot of digital logic design, and here we are trying to see how can you use this digital logic design concepts to build, or I would rather say to start building a computer, right? So this is in no way that advanced. And the second option is, apart from Harris and Harris chapter 6 and chapter 7, you can also take a look at Morris Mano, which was the textbook for this course. And they do a lot of treatment of processor design from chapter 9 to chapter 12, I guess, or at least chapter 9, 10, and 11. Chapter 8 has things related to register transfer, and which is also something that I have taught in the previous lectures, right? All this register transfer logic, the tri-state buffers, the bus architecture is going to be covered as a part of chapter 8 in Morris Mano. Chapter 9, chapter 10, and chapter 11 primarily deals with the content of a processor design, instruction sets, processor design, and so on. So you can either follow that, that is going to be a more generic discussion. It's not going to really going to construct a very specific processor. They are going to give you ideas of the best practices or the various concepts that needs to be known around that area. And the other option, I think this is a concise and effective option, is to follow this book by Malvino, and Brown, if I am not mistaken. And this book, right, we have to look into the specific chapter, is called SAP 1. And then there is a chapter called SAP 2, and there is a chapter called SAP 3. And even before SAP 1, they are going to, this is again a digital logic and computer design textbook, but they are going to make these three chapters very specific to a particular design, right? So that you get a very concrete idea of a specific design. And while discussing SAP1, you have to use components such as registers or counters and other things. So they have already been introduced in the previous chapter. So wherever you find that, okay, in the design of the control circuit, you need a ring counter, right? And you have been taught how a ring counter works, and all you need to do is just revise that concept, or just go to that chapter that discusses about the ring counter implementation, let's say using JK flip-flops, and you just check that how this ring counter could be used in the design of the control logic. So I would recommend this Malvino and Brown for the computer design part. This is not going to be overwhelming, right? It's not comprehensive. You are not going to know a lot of different aspects, but at the same time, it is concrete enough and is going to give you a high level understanding of the working of a computer, right? And this is in no way going to compensate for a regular computer organization and architecture course, right? Typically, this is offered as a separate follow-up course based on the concepts of digital logic design, right? Here, as a part of, we call this course as computer system design, we try to give an introduction of both the things. We try to be more elaborate on the digital logic design part, particularly combinational circuits and sequential circuits, followed by a computer system design intro, where we try to borrow this combinational circuit and sequential circuit structures to implement a computer. Hope that gives you an overall idea, right? So now we will focus our attention to our architecture, which we call Gajendra ALU, Gajendra CPU. And as you can see, this has, we are not going to consider this register X for now. We are going to have three registers, registers A, register B, and register C. We are going to have this ALU that is capable of doing two things. It is going to do an addition and it is going to do a subtraction. I am going to teach you how subtraction works, because I have not formally introduced any computer arithmetic yet. But you know how addition works, right? We have introduced how a full adder works and how a ripple carry adder works, where the carry is propagated uh, through every bit position. And using a full adder, you can have n number of full adders to create a n bit full adder. And we are going to see how to also create an n bit, you can call it full subtractor if you want, right? So it just not does a plus b, it is also capable of doing a minus b. And there are some conceptual uh, things that has to be introduced in order to know how subtraction might work in a computer circuit. So these are the two things that are going to be supported in our Gajendra ALU. Then we are going to have a program counter. The program counter counts the basically it points to the instruction that is going to be executed next. So program counter or PC, it is just a side note, is the term is still there because of historical reasons. Uh, there are a lot of opinions about what this particular counter is to be called, and often you will find references where they call this program counter also as the instruction pointer. So this is also an Intel terminology. Intel computers often they have this particular entity which is equivalent to the program counter. They call it an instruction pointer, which is logical, right? The instruction pointer is typically pointing to that instruction, and in essence, it is storing the address of a particular instruction. So it is actually a pointer, right? So it's an instruction pointer, and the instruction pointer points to a specific address in the memory, and the value is going to be stored in the instruction register, which is the actual instruction. For the memory, we are going to keep it very, very simple. our memory is going to consist of only 15 bytes, 15 bytes, okay, and this is byte addressable. So every location is a single byte, and you have 15 or 16 bytes rather, sorry. So it is going to start from 0 0 0 0 and it will continue to 1 1 1 1, which is f or 15, and together you are going to have 16 bytes, okay. So if you want to address this 16 bytes, you can always imagine that how many bits are needed. So how many bits are needed to address 16 bytes? 4, right? 2 to the power 4 is 16. From this very fact, you can understand that the memory address register is going to contain 4 bits, right? This is 4 bits, right? uh, and the program counter is also going to have 4 bits, okay. This is very important. 4 bits is the size of the address. You have to be very careful about this thing. 4 bits are necessary to point to a particular byte in the memory, and that byte could either be an instruction or be a data, and we only have a unified memory for both the program, the instructions of the program, as well as for the data that the program might be using, okay. So there is no other extra memory that we are going to consider as a part of this construction, okay. So now coming to the memory, if you issue this 4-bit address to the memory and read from memory, the data that is going to be coming to the common bus is going to have a size of how many bits? We are storing 16 bytes, right? And every byte is addressable by this 4-bit address. If you read one particular byte, there are 8 bits, okay. So you need to be careful about the interaction of the program counter and the memory address register or MAR with the common bus, because the common bus is going to be carrying both addresses as well as data. So this is going to have 8 bits, 8 bit, I would say, data path, okay. But whenever you are setting the values inside the memory address register or the program counter, we need to be careful about how these bits are manipulated. So we can have a convention that maybe the last or the least significant 4 bits are the part of the address, or somehow, right, some kind of an agreement has to be there, right, because only 4 bits is meaningful here, whereas here also only 4 bits are meaningful, okay. So you can always pad the most significant 8 bits with 0. That is an implementation question, but you need to take care of this, okay. So this is important. uh, Whereas memory is going to spit out 8-bit data, right. Instruction register can also be provided with this 8-bit instruction, right. There is a debate about this, right, whether we want to send the operand also to the instruction register, or we are just going to send only the uh, operation part. We are going to come to that in the next slide, but overall I think these are the things that we have to keep in our mind. So we talked about the registers, we talked about the ALU, we talked about the status registers, we spoke about program counter, we spoke about the memory, we spoke about the MAR or the memory address register. We also spoke about the instruction register, often called IR, okay. This is MAR, IR, and this is called PC. And these registers, we are going to call them as reg. Let's say reg underscore A. This is reg underscore B. This is reg underscore C, and so on, okay. So and then the most important component is the processor or CPU, controller. Okay. Okay, so the controller is going to be connected to the clock, and every clock cycle it is going to do something, right? And a particular instruction may require a sequence of all these moves, right? As I told you, there is a fetch operation, there is a decode operation, and there is an execute operation. Depending on what kind of operation is being executed, it might require a small finite number of this ordered sequence of operations, right? And some of those operations has to be mutually exclusive, right? So they cannot take place at the same time unless and until we consider things like pipelining and so on. We are not going into that regime, right? This is something which is non-pipelined, means that you cannot have instructions being executed in parallel. Okay, we are not touching that because that is again an advanced concept. I won't say advanced, but uh, this is something that we are not considering given the timing restrictions of the course, right? We want to make you understand something very simple but make you understand in a very concrete way, right? uh, if you understand this very well, it is not going to take you much to have a pipelined implementation of the same processor. Okay, so we are not considering a pipelined CPU. This is a serial thing, and it's going to consist of multiple clock cycles to execute an instruction. Okay, you can call it a multi-cycle CPU, where clock is provided to the control signal, and with the edge trigger of the clock, every edge trigger of the clock, a control word is issued, right? A control, here they are issuing a control word, and you may require uh, 5 or 6 or 7 control words to execute an instruction. Okay, this is very important and very critical. I am telling you this qualitatively now. Later when we look at the implementation, these concepts is going to come back again. So for now I will summarize that the controller part of the CPU is responsible for orchestrating the different data movement operations inside the CPU while executing an instruction. Okay, don't think that once you know you have to do add 5, just in the blink of an eye add 5 or add 7 is executed, right? There are a series, as I told you, starting from the fetch cycle. There are a series of small baby steps that needs to be executed in sequence in order to achieve this. And suppose you need 5 such things in the sequence, each one of this step is achieved by issuing a control word. Okay, so for uh, achieving the add operation in our context may require 5 control words to be executed one after the other, or issued, I would rather say, issued one after the other. So it will require 5 clock cycles. So every clock cycle 1, you issue a control word. Clock cycle 2, you issue the next control word. Clock cycle 3, you issue the next control word. Clock cycle 4, clock cycle 5. After you are done with clock cycle 5, maybe you are done with the instruction add 5. Then what is going to be done? Then it is going to again increment the program counter, fetch the next instruction, and continue like that, right? So the control part is going to orchestrate how an instruction is executed, and of course how a program is executed overall, because it is also going to control the program counter, right? So this is sort of the actual brain, right? So if you think that CPU or the processor is the brain of the computer, the controller of it is basically the brain of the brain, right? So it's the main hub where all the control signals are generated and everything else is orchestrated, right? This is the lifeline of your processor, right? Otherwise, if you take out the control, the processor, they are just have the registers and all the hardware lying around, but they don't know. We don't have a way to activate them in a meaningful way to do the computation, right? So always remember the control signals is one of the most important part of the CPU. Okay, and we are going to learn how to design this controller in our small scale setup.